Yeah, just kind of an application, I guess, of the integral. You know, we talked about the integral. The integral's the area under the curve, net area, if you got above and below the x-axis. So we know that, but what about application of it in other terms, I guess we might say. Well, let's just hypothetically say, all right, so let's say we've got a velocity function, call it v of t, and we integrate that. Well, what we know is that when I do this integral, if I can do it anyway, figure it out, when I get my value here, it's the antiderivative of this, right? So let's think through that. I've got the velocity, and I do the antiderivative of that. What would that put me back to? Got the velocity, and I do the antiderivative. Well, think back when we started talking about derivatives. All right. In derivatives, we took like y equals some position, gives you some position, or height, right? Something maybe like that. If that gives you a position or height, the derivative gives you the velocity, doesn't it? Right? Take the derivative of your position, that gives you your velocity. And take the derivative of that, that gives you the acceleration. Remember doing that? Well, here we're going just the opposite, aren't we? We're taking the integral of v of t, so that's going to give me, this is going the other way, right? Gives me the position. So it gives me the position function. And then I go from t1 to t2. And so if I plug those in, let's think about what that gives me. So I take the position at t2 minus the position at t1. What does that give me? So the position at t2 minus the position at t1. I'm taking the difference of that. So that's the difference of the positions, T2 and T1. So it's the displacement, if you will. That's what they call it. Now, the thing about it is, it may be, so here's T1 height, position, and then, whoops, that's what my paper's all over. So I've got T1 height here, and then T2 height here. And so I'm finding that difference. Now, does that mean I've just traveled from here to here? Maybe not. I may go from here, then it goes up, and then it comes back to here. You see what I'm saying? So that gives you kind of the net displacement. It doesn't give you, because it's really traveled a little further, it just gives you a net displacement from one time to the other time. Because it may have gone all sorts of other heights or positions between those, but okay. So that sort of ties in, you know, we said that the integral gives me the net area, so this gives me a net displacement. Kind of the same idea, but that's one example of what this gives me. If you've got the velocity, you take the integral of the velocity, you wind up, the definite integral, you wind up with a displacement, because it's basically gives you a position. This velocity integral gives you a position because you're doing the antiderivative. You're doing the opposite of your derivative, okay? Well, to put it more generic terms, I guess. So velocity, we said, another way we can describe that is a rate of change. So if f of x is a rate of change, function, the integral a to b f of x dx, which would be, when we do the antiderivative, big F of b minus big F of a, big F's the antiderivative. What that gives you is, well, using our example here, that gives me, if that's a rate of change, that gives me then the net change of F of our big F, whatever it is, from A to B. It might be even, let's do this. Let's change this to f prime of x, just to make it obvious. Rate of change is usually a derivative. All right, so that would make that the antiderivative there, which would, if we do the antiderivative, then it's, then we're back to, just regular f, you see. This is the derivative, so the antiderivative we got. Because that was the other example was more in line with those terms. If d prime of t is the rate of change of the volume, then what is the integral t1 to t2, whatever time values you want, of that v prime dt, what does that give you? Well, we're doing the integral of the v prime, so that's going to get us back to just regular volume, isn't it? So that's going to give me a volume, if you will, function. And then when I evaluate it from T1 to T2, that's going to be the change in the volume, following our example here. So that would give me VT2 minus VT1, if you will. If I do the antiderivative, it gives me the volume. Plug in the T2 and T1. And so that's going to give me that change in the volume, the net change in the volume. So, anyway, don't know if that makes any sense or not, but that's what it does represent in terms of some application, if you will, of interval.